Hello, nice to meet you. My name is Lim Sunglock. I am from Osaka University. Today, I will talk on application of FactSage to design lunar resource processing in lunar metallurgy, as shown in the title. Firstly, I'll talk about background of application of FactSage to lunar metallurgy and calculation condition for FactSage. And next, I will introduce our results of FactSage calculation. We investigate the equilibrium phase and viscosity of lunar soil using FactSage. And then the conclusion will be followed. This page, I will explain background of application of FactSage to lunar metallurgy. We are currently studying and trying to get the metallic ion from the lunar soil on the moon surface. The moon surface is usually divided into two phases, the dark phase and bright phase. The dark phase is called merism, and the bright phase is called hyalandrism. The merism is mainly composed of basalt, which is a mixture of these minerals. On the other hand, the hyalandrism is mainly composed of anorthosite, which is a mixture of fragile classes. As you can see, merism contains various metal components such as iron and titanium. So we are focusing on the metal basalt region for lunar metallurgy. This table shows the chemical composition of metal basalt region. Silicate oxide is the main component, and iron oxide is about 15 to 28%. In particular, titanium oxide is also contained in the basalt, and the content of titanium oxide varies greatly depending on the location. At this time, our goal is to extract metals from metal basalt region for lunar metallurgy. So it's necessary to know the equilibrium behavior of metal basalt at high temperature and the low oxygen partial pressure. However, metal basalt is the multi-complex compounds. Therefore, FactSage calculation was applied to investigate the equilibrium behavior of metal basalt at high temperature. We applied the FactSage calculation to our experiment to lunar metallurgy. This table shows the chemical composition used in our calculation. We selected this composition for lunar metallurgy. And then based on this composition, we obtained this calculated result. As you can see, the metallic ion is produced at about 1050 Celsius degree. Based on this information, we conducted FEO reduction experiments to get the metallic ion. And we successfully obtained the metallic ion from the regular stimulant by experiments at around 1000. After that, we hit the specimen up to 1600 Celsius degree. This figure shows the metallic ion in molten slag produced after our experiments. The reduced metallic ion exists as fine particles, and the particle size is several micrometers. And we are now considering various processes to aggregate the metallic ion particles in molten slag. Therefore, we conducted a FactSage calculation to obtain various information of molten slag. In addition, as shown in this figure, there are two slag phases in this temperature, slag 1 and slag 2. As shown in the previous slide, there are two slag phases, slag 1 and slag 2 in high temperature. As a result of analyzing the composition of slag using FactSage, slag 2 was a compound of titanium oxide. This is very important information because, as I mentioned before, bare basalt contains 1 to 14 weight% of TiO2. So the formation behavior of slag 2 might depend on the concentration of TiO2 in the slag. So if the slag exists in two phases, we need to know the composition and viscosity of each slag. Therefore, we applied FactSage calculation to investigate the equilibrium behavior of the lunar basalt and the viscosity of molten slag. This table shows the calculation conditions. We selected this composition as the standard composition on the basis of the information obtained from Apollo 11 data. And based on standard composition, FeO was fixed at 15.5 mass%, and TiO2 was changed by every +2% and every -2%. The rest of the components changed at the same ratio with the change of amount of TiO2. And we calculated it using FactSage under these conditions. These two figures show the result of calculation. The left side for the standard composition and the right side is for -2% of TiO2, which means that TiO2 content 2% less than the standard composition. For the standard composition, there are three phases at 1600 Celsius degree: slag 1 and slag 2 liquid phase. On the other hand, in this figure on the right, there are only two phases, slag 1 and liquid 1. There is no slag 2 in right figure. Therefore, as the amount of TiO2 in slag decreases, slag 2 disappears. In the case of -4 and -6, -8% of TiO2, we obtained same results as -2% TiO2. On the other hand, let's compare the results where TiO2 increases. When the TiO2 increased by 2%, we can see that the amount of slag 2 also increased like this. In addition, the formation temperature of slag 2 decreases. In standard composition, slag 2 starts to form at about 1500 Celsius degree. However, in this case, it can be seen that slag 2 is formed at approximately 1450 Celsius degree. Similarly, when the TiO2 increases further, +4% and +6% of TiO2, we can see that the amount of slag 2 increases like this. In addition, whenever TiO2 increases, the formation temperature of slag 2 decreases like here. Then let's see the composition of slag and liquid phase for +6% of TiO2. We analyzed the composition of slag and liquid phase. The major component of slag 1 is silicate oxide. And in the case of slag 2, the major component is Ti2O3. The liquid phase is Fe-Si Ti solution, and the major component is Fe. And at this temperature, the Fe alloy is in the liquid phase. As I mentioned before, there are two slag phases in these conditions. So in order to design a process for aggregation of small metallic ion particles in slag phase by such as mixing, the information on the viscosity of molten slag is necessary. Therefore, the viscosity was calculated using FactSage in these conditions. And we intend to aggregate metallic ion at 1600 Celsius degree. So viscosity was calculated under this temperature. This page shows the calculation results of viscosity on the standard compression and plus 2% TiO2 condition. For the standard condition, the viscosity of slag 1 is about 7.32 points, and the viscosity of slag 2 is about 1 voice. The composition of each slag is as follows. The main component of slag 1 is SiO2, and for slag 2, the main component is Ti2O3. In the case of plus 2% of TiO2, the viscosity of slag 1 is slightly increased. On the other hand, slag 2 does not change it significantly. And the composition of each slag is similar to standard conditions. In the case of plus 4% and plus 6% of TiO2, the viscosity increased slightly to 8 and 8.4 voice. However, slag 2 is almost constant. The composition of each slag is similar to previous one. This left figure shows the viscosity tendency with TiO2 contents. The viscosity of slag 1 increases slightly as the amount of TiO2 increases. On the other hand, slag 2 has amount constant value regardless of the amount of TiO2. And the right figure shows the change in the amount of slag and liquid phase. We can see slag 1 decreases linearly as TiO2 increases. However, slag 2 increases drastically as slag 1 decreases. In the case of slag 1 is the main components are SiO2, Al2,3, CaO, MgO6, and slag 2 is Ti2O3, SiO2, CaO, MgO6. For liquid is Fe-Si solution. This table shows the proportion of slag 2. In the standard composition, there is small amount of slag 2. However, as the amount of slag 2 increases, the amount of slag 2 increases largely. That's the conclusion. Firstly, in order to perform an experiment to extract metallic ion from the lunar regolith, FactSage calculation was applied to understand the melting behavior of lunar regolith at high temperature. And based on the composition of lunar regolith in the Melba South region, the equilibrium phase and viscosity of lunar regolith were calculated with the amount of TiO2. At high temperature, slag is separated into two phases, slag 1 and slag 2. And the amount of slag 2 increases as the TiO2 content increases. Lastly, as the TiO2 content increases in the standard composition, the viscosity of slag 1 increases, but slag 2 is constant. So I think FactSage is a powerful approach to design lunar resource processing in lunar metallurgy. Thank you very much for your kind attention.